already saw that we can use the R program instead of using a table, using a normal table that we can find on the internet. One advantage is that this is more precise, although it's not exact. Another advantage is that if we have the exact value that we want, then we can just type it in. For example, I said that the good thing about normal is that it can be normalized, like it can be standardized, but then if we use an R program, we don't even have to standardize it. For example, here, I said that we can standardize a normal variable that looks like that, with a mean of 70 and a variance of 8. Then in my R program, note that in my R program, it wants me to give a standard deviation, not the variance, and so I have to take the root of it. So I believe the function was square root. So I'm not typing. Square root of 8, and I get, so I don't have to type this in a calculator or anything. So maybe I want the probability that if the mean is 70 and the standard deviation is 8, then, and the failure is at 59, so I need a score of above 59, then maybe I can type p norm 59, the mean is 70, and the standard deviation is square root of 8. Then this is the probability, a very small probability of me failing. So I didn't have to normalize everything. Maybe I could do 65. Notice that if it's 70, then it's exactly 0.5 because it's exactly in the middle. And it's a symmetric distribution. So that's the good thing about using R. We don't have to normalize it, even though we can. And we can turn it into a distribution of 0 and 1. Furthermore, we can use other programs associated with it. But before that, I'll teach you one more function, Q norm. So I think Q stands for quantile. And for P norm, I had to give a quantile and then the mean and the standard deviation. And it gives me how much of the area is underneath the curve there. For the Q norm gives me the quantile, but I give the the probability from negative infinity to that number, P. To that number, Q, and if I want that area, then the Q norm will give it to me. For example, if I do Q norm of 1.96, 0, 1. Why does it not work? Mean 0. Sorry. So it needs to be between 1 and 0 and 1, right? Because it's a quantile. So 0.95, 0, 1, 0.975, 0, 1. So notice that this value is very close to 1.96. 1.96 is used in a lot of journals because if we look at the table here and I find the value 1.96, so I'm looking for 1.9, and then I have to go across till 6, so that'll be this column right here. The answer will be here. If I draw this, so what's happening is that if I have a standard normal, mean 0, variance 1, so standard deviation 1, and I plot 1.96, then this area remaining is going to be 1 minus the number that I highlighted. it's 0.475, right? But then the Wikipedia one, as I said before, only goes from 0 to that number. And so this area from here to here is 0.475. The remaining area is 0.5, and so if I add it together, I'll get 0.975. So what's remaining is 0.025. Okay, this much of the area is remaining here. Likewise, if I go to negative 1.96, I'll have 0.025 remaining here. And so if I add these two, then I'll get 5%. And in journals, you're going to see, for example, significant at the alpha is 0.05 level. I don't have time to cover everything and say what this means, but hopefully you remember this from introductory statistics classes from undergrad. But anyway, that's why this number 1.96 is helpful. But then R is better because instead of using 1.96, this estimates to the, it gives 7 significant figures, and it turns out it's not exactly 1.96, it's 1.95996. But anyway, we can give a value that we want, significance value that we want, and then get the exact quantile. Okay, and we can do that for the normal. But we could also have done that if our average was 70 and my standard deviation was, for example, 5, then the top 2.5% has a score of 79.79982. So this is how we use the R program. There are also other functions like R norm, D norm, but we won't do them for now. I think Q norm and P norm are the most often used. Okay, so now we don't have much time remaining, so I might be in a hurry. And everything's important, so I don't know what to skip. So, usually for the standard normal, if we have a mean 0 and standard deviation 1, then instead of writing a random variable x, we write the random variable z. So z is actually reserved for the standard normal. So if we have a lot of z's, so for example z1, z2, etc. If all these zi's from I is 1 to k, if they are independent, magnetically distributed, and we square each zi, and then we sum them up, then this is also another random variable, right? Notice that in this random variable, we can never get negative, because in the normal, if we land somewhere here, then this negative value gets squared, and so we end up with a positive value. And we're summing them from I is 1 to k, and so this is also another random variable, but it's always positive. And this has a special name. This follows the chi-squared variable and degree of freedom k. Okay, and this is used often in econometrics. So I'm just going to mention that something like this exists. Furthermore, back in the old days, I think they had to, just as we searched the table for normal, they had to do a chi-square table. But the chi-square table is not as good as the normal table because we have a degree of freedom, and depending on the degrees of freedom, the p-value or the probability that it's between negative infinity and that value is always different for all the different degrees of freedom. And so Wikipedia chose different sets of important numbers. But what if our number is not here? That's why we use R. So just as we use P norm and Q norm, we can use Q chi squared. And it tells us that inside Q chi squared, I give them the P. For example, to give like 4, and the degree of freedom might be 3, so I'm adding 3 normal variables that are squared to each other, and I'm adding them up, and it's all another random variable. And if I do this, why is it wrong? Yes, I made the same mistake as before. So P has to be between 0 and 1, right? So if I want the 95th percentile, then it's 7.814. If I draw a chi-square variable, actually I won't draw it, I'll show you pictures of chi-square variables. They look like this. So depending on the degree of freedom, the chi-square variable moves. It moves to the right, which makes sense because as we add more and more random variables, the mean is going to shift up, right? So right now, when I told R to do Q chi-square of 0.95 and 3, what it did was it made k equal 3, so we're using the teal line, right? We're using the teal line, and it's telling me that at 7.8, at around here and above, we have 5% of the total area, and below 7.8, we have 95% of the area. Okay, that's what R is telling me. Similarly, I can do P chi squared, but then if I add in the number that I got before, 7.8, then I expect to get about 95%, right? Which is what I get here. If I want to be really precise, maybe inside here, I can type in P chi square of Q chi square of 0.95 and 3, but note that P chi square and Q chi square are kind of like inverses to each other, and so we just get back 0.95. So hopefully this makes sense. We are calculating the number at which we get 95%, and from that number, we are calculating the percent, and so we get 95% of the graph below that number. Let's see. Okay. Next, we have the t distribution. Okay, so this was chi squared. This X-looking thing is actually a Greek letter called chi. That's why it's called chi squared. Okay, next we have the t distribution. So we need 3 facts to make the t distribution. We need to have a normal, standard normal. We need to have another one, y, following chi squared of degree of freedom k. And finally, we need them to be independent. And if these 3 facts are true, then z, then t, which is z divided by the square root of y divided by its degree of freedom k. This follows the t distribution of degree k. So I wrote t twice, so that might be confusing. So maybe I'll write capital T. This follows the t distribution of degree k, sometimes called the student's t distribution, because the person who found the t distribution didn't want his name published, and so student was his pseudonym that he used to publish his work. So how does the t distribution look like? One important thing about the t distribution is that it's more accurate than the normal distribution in some sense. for research purposes. So T distribution, students T. Okay, so this is what the T distribution looks like. In fact, it looks very similar to the normal, and as the degree of freedom goes to infinity, we get the normal distribution. And as the degree of freedom goes more down, then we get a normal looking distribution, but not exactly the normal, with a fatter tail. So maybe the T distribution is better in that it accounts for more outliers. Okay, so there might be more outliers when distribution follows the T rather than the normal. So we have to remember that as K goes to infinity, as the degree of freedom goes to infinity, T goes to the normal distribution, but then the convergence is in distribution. Maybe I'll have time to talk about what convergence in distribution means, but basically the distribution is going up to the normal. Okay, and the R, so I have PT and QT. So for QT, maybe I can have the probability will be 0.95, degree of freedom might be 4, right? And then it gives me the value. And if I raise the degree of freedom to like 50, then I get another value. If I raise it more, then I will end up with a degree of freedom that looks much like, if I raise the degree of freedom, I'll get a value where the quantile for the 95% goes to the normal. So since the degree of freedom is so large, then we can basically use the normal. I think statisticians say that when the sample size is greater than, or when the degree of freedom is greater than or equal to 30, then you can approximate using the normal. Maybe we can check, see if they're similar. So they're not that similar, but I guess this number is small enough, or the difference between these two numbers, QT and Q norm, are small enough that we can approximate our T distribution using the normal. But if we have a computer, if we have our program, there's actually no reason for us to approximate using the normal. In fact, it takes longer to type this. Just type T, and it gives us the exact number here. So T distribution is important because sometimes our sample size is not big enough. We talked about a random sample, but if the sample size is small, then we can't use the normal to approximate. We need fatter tail because, for example, if we had 100 Asian heights as before, this might have, if we pick 100 different Asians, then we might end up with another distribution or another height that's very different from our previous average that we had before with 100 people. And so there might be too much variance in there. There might be a fatter tail. Fatter tail implies a shorter mode, right? Because all of their probabilities have to integrate to 1. Are there any questions about the T or the chi-squared? Okay, so right now I'm just introducing different common distributions so that later when you see them in literature, you'll feel familiar with them. So now let's talk about the F distribution. Also used a lot in economic research. So the F distribution is as follows. If I have two distributions, each of them following chi-squared. So chi-squared of k1. This follows chi-squared of k2. And I take the ratio of the two if y1 and y2 are independent. And I divide y1 by its degree of freedom, divide y2 by its degree of freedom. Then this follows the F distribution. But then in the parameter, in the t parameter, there was only one of them, right? We only had to account for one degree of freedom because the z is always a z. But then in F, we can change the degree of freedom for the top and the bottom. So here and here. And so it takes k1, k2 as its values. So again, the chi-squareds are a sum of the squares, and so it can never be negative. And F is a ratio of the chi-squareds, and so it can never be negative. In R, just as we did QT and PT, we can do QF and PF. See, if you notice, the good thing about R is that if I type in QF without anything, then it tells me what to put in. It says QF of, and I put in P, degree of freedom 1, degree of freedom 2, and then these other values are default values. It says if something's missing, then do whatever. So you can search up what each of them mean. This lower tail means instead of finding the area between 0 and that value, we are finding the area from that value until infinity. I said 0 instead of negative infinity because it starts at 0, right? So maybe I can say lower tail equal false if I want that, or I can do 1 minus the function. Anyway, if I do QF of, for example, 95%, degree of freedom for the first one is 3, for the second one is 5, then I get this value which means something. So I guess if our alpha level is at 5%, then my F statistic has to be bigger than this number for my result to be significant at the 5% level. So again, in the old days, we had to use an F distribution table. But then the table is really bad because it only gives us select values of the P. So look here. It gives me 0.1, 0.05, 0.025, 0.01, and 0.001. It gives me different values when my first degree of freedom in the numerator is at 3. So remember, I did 3 and 5. So in the table, I would have to search 3 here and 5 in the denominator. And my value will be that number right there because I'm at the 0.05 significance level, right? Is that right? 5. Oh, actually, it'll be this one, sorry. 1, 2, 3, 5.41. Can you see it, or should I zoom in a little bit? So degree of freedom for the denominator is 5, for the numerator is 3, so it's the third column. We're at the 0.05 significance level, and the table gives me 5.41. So my F statistic has to be bigger than this. But I can use my R code and just get this, and instead of 5%, maybe I can do 4%, and it'll give me another value which I cannot find on the table here because there are only 1, 2, 3, 4, 5 values that the table gives me, because the table can't be that large because there are 2 degrees of freedom involved here. So that's why my advice is to, although I'm not in a position to give advice, I think it'll be better to always use the R code whenever we can, because it's a lot more convenient. Okay, so now let's discuss the gamma function. So a good mathematical text to refer to is Rudin's principles of mathematical analysis. Very famous text. It might get referred to a lot in economic texts as well. Also labeled PMA, sometimes called Baby Rudin, because Rudin wrote 3 books, and this is the easiest book, which is not very easy. It's very dense. So to learn mathematics, it might be bad to start with this book, but to review it or to get some references, this book is a very excellent book to do so. So a gamma function for positive numbers is defined as follows. This is the Greek letter gamma, and it's the integral of t to the x minus 1 e to the negative t dt. This is the gamma function. And so my integral is actually a function. So if I plug in gamma of 1, I'll get 0 to infinity of t to the 0, so just negative e to the negative t dt. And if I use integration by parts, I won't do it here because I did something similar on the first day. I'll get 1. Or actually, do I even need integration by parts? I don't think I need integration by parts. I can just do it straight away, right? Using chain rule. So this will be negative e to the negative t from infinity to 0. So the limit as t goes to infinity is 0 because it's a negative infinity. So it's 0 minus negative e to the 0, which is just 1. So gamma of 1 is 1. And furthermore, we can check that gamma of x plus 1 is x times gamma of x. So it's recursively defined. Then gamma of 2 will be 1 times gamma of 1, which is, and I know gamma of 1 is 1, so this is 1. Gamma of 3 is 2 times gamma of 2, which is 2. Gamma of 4 is 3 times gamma of 3, which is 3 times 2, or 3 factorial. Gamma of 5, I think we know where this is going, is 4 times gamma of 4, which is 4 times 3 factorial, which is 4 factorial, and so on. And so gamma of n is n minus 1 factorial. So in some sense, this gamma function is a generalization of the factorial. The factorial is only defined for integer values, but gamma is defined for all the values in between. So this is a useful function. How is it related to probability? But before I say that, I'll just make one important theorem that I'll state and not prove. So theorem, we have f of x is the gamma function of x if and only if, which we learned about on the first day. If and only if. What I proved just now, gamma of x plus 1 is x times gamma of x. B, f of 1 is 1. Maybe instead of writing gamma, I should write f. And C, log of the f function is convex. Convex, we discussed also, using Jensen's inequality, right? Okay, so I think this is the most important theorem with gamma function. Gamma, if we have a gamma function, then it satisfies these three properties, and it is the only function that satisfies these three properties. Okay, and now let's talk about the gamma distribution. Okay, so the gamma distribution is as follows. So I'm just going to write gamma function on top. Don't confuse this with the distribution, because the distribution just follows. X follows gamma distribution of alpha and beta if my PDF, sometimes this is written in this manner, in Casella-Berger, it's written in this manner, because I'm given alpha and beta. Just as in the binomial, I was given n and p, in gamma I'm given alpha and beta. F of x is 1 over gamma alpha, beta to the alpha, x to the alpha minus 1, e to the negative x over beta. And this is a very complicated function because even the gamma function is a complicated function that we see here. But then we have to do some more in this. And so nobody actually integrates this, but if you're interested, you can refer to a text. Again, in the R, we can write P gamma and Q gamma, and then do the same thing. I won't do it here, but we can do the gamma like that. And then from the gamma, we can make some distributions. Okay. So, for example, we can make, I think it was the beta distribution. Right? So if I'm going to make another function, and this can be found in Casella-Berger's text, page 106. If the beta function looks like this, it's an integral from 0 to 1 of x to the alpha minus 1 minus x to the beta minus 1. Then we can check that this beta function is related to the gamma function in this way. Beta function of alpha and beta will be gamma of alpha times gamma of beta divided by gamma of alpha plus beta. So this is the beta function. Similarly, we're going to define a beta distribution. So x follows the beta distribution of alpha and beta. So remember, up here I defined the gamma function, which was different from the gamma PDF. The gamma PDF had a gamma function in it, but it's not the same as the gamma function. Here, similarly, I'm going to define a beta PDF, a beta distribution, that uses the beta function, which can be defined in terms of the gamma function, but it's different in that the second one, the blue one that I highlighted, is a PDF. So the PDF looks like this, f of x, given the parameters alpha and beta, is 1 over the beta function of alpha beta times x to the alpha minus 1 minus x to the beta minus 1. But the x's have to be between 0 and 1. beta distribution is used to compute the ratio of waiting times, for example. But we won't discuss more about the beta function. But just so that you get used to it, in any statistics course, starting from mathematical statistics 1 and 2, in the undergraduate courses in the applied statistics department, they always teach this because they have a name for a reason. They're famous for a reason. Okay? And as a counterexample to the non-existence of expectation, to the existence of any random variable being less than infinity, there is something called the Cauchy distribution. And the Cauchy distribution takes the parameter theta, but for now, let's not think about that. Let's just think about one example of a Cauchy distribution, which is 1 over pi, 1 over 1 plus x squared. First of all, is this a distribution for all real numbers? Is it? Sorry, it's 1 plus x squared. First, note that this is pi is positive, so 1 over pi is positive. X squared is positive, so the denominator is never 0. And so f of x is always non-negative. Okay. Second, I have to integrate this over r, and this has to equal 1, right? So if I integrate 1 over pi, 1 over 1 plus x squared dx, does anyone remember how to do this? We have to use the fact that the derivative of the arctangent is 1 over 1 plus x squared. And if you don't remember it, we covered it yesterday, so you can review yesterday's notes. So the integral of 1 over 1 plus x squared is just arctangent. And it's from negative infinity to infinity. And so the answer is 1 over pi arctangent from negative infinity to infinity. Note that the standard way to cut a tangent function to make the arctangent a well-defined function is to cut it from negative pi over 2 to pi over 2. And so tangent as x goes to pi over 2 could be plus or minus infinity because there's another one, but because of the way we cut it, maybe we can say this is infinity, and this is bad. You shouldn't write this, but I'm running out of time, so I'm not going to write the limits. This is negative infinity. And therefore the arctangent at positive and negative infinity is pi over 2 and negative pi over 2. And therefore we have 1 over pi of pi over 2 minus negative pi over 2. And I get 1 over pi times pi, which is 1, as desired. Okay, so this is a Cauchy distribution. But the expectation doesn't exist. The first moment doesn't exist. It is not true that this is less than infinity. Okay. Let's see why. What is the definition of the expectation? It's the integral of the function, and then I add an absolute value, right? Because I'm taking the expectation of the absolute value. I think I'm using the fact that I'm putting an absolute value here because because this is the definition of the first moment, which is x to the 1, does not exist. Does not exist. I think this is how Casella-Berger defines it, because if we do the negatives, then they might cancel out and we get 0 because it's centered around 0. But if we do the absolute value, then this is the same as not from negative infinity to infinity, but from 0 to infinity, but twice of that, right? Of x over pi times 1 plus x squared dx. Remember how to differentiate log? It's 1 over x. And so if I differentiate the log of 1 plus x squared, then I can use chain rule and say this is 2x over 1 plus x squared, which is exactly what we have here, right? And so if I integrate this, then I'll get 1 over pi log of 1 plus x squared from 0 to infinity. If I plug in 0 into x squared, then I'll get log of 1, which is 0. If I plug in infinity, then the limit as x approaches infinity, the log of 1 plus x squared. Remember, even though log is a slowly increasing function, still it goes up till infinity. And so the limit doesn't exist. And so this doesn't exist. It's not less than infinity. And so the Cauchy distribution is a distribution where the average, the mean, doesn't exist. And I think this happens because the tail is so fat. So remember, if this is the normal, then the t distribution has a fatter tail, but the Cauchy distribution has an even fatter tail. And when we take the average of everything in the Cauchy distribution, when we take the average of everything, then we get outliers so often and such big outliers that we can't do an average on it. I think that's the intuition that we should get from the Cauchy distribution. There are other distributions that are discussed in economics, but I think this should be enough for you to study on your own. I wanted to mention the central limit theorem and the law of large numbers, but to do this, we have to talk about convergence. And convergence is a topic that's kind of hard to understand at first. It's taught in real analysis. If you really want to understand what the central limit theorem and the law of large numbers, the weak law and the strong law of large numbers, what they're saying, I think you should first look at what convergence means in mathematics. And there are different types of convergence in probability. There's convergence in probability, convergence in distribution. Convergence, almost surely, there are these different types of distributions, but it's hard to understand them if you don't know what regular convergence in mathematics means. So I encourage you to study convergence first before learning about the central limit theorem and the law of large numbers, which are arguably two of the most important theorems in statistics, or at least at the beginning level. Okay, so I'll end class here, and thank you all for staying with me till the end.